Okay, let's talk about fuzzing. As I promised in the last class, well, the demo gods killed me, and so I hope this time we'll get this. We'll get through this. Anyway, the objectives for this demo video: talk about fuzzing again, just reiterate what I talked about in class. Then I'll get into the AFL tool, and then we're going to be fuzzing a goat. So, what is fuzzing? It's an extreme form of negative testing using a tool called the fuzzer. This is where we have continuous inputs of randomized data. And usually fuzzing happens over long periods of time. They're called campaigns, but we'll get into that more of what a campaign is. And then we're looking at any kind of input that your program may have. It might have an API, it might use files, read files, perhaps command line arguments. All of those are potential targets. And what we are really looking for is unexpected behavior where input is not sanitized. I'll talk more about that as well. That's very important. Now, there's various types of fuzzing methodologies and tools out there, but today in this demo, we're going to be focusing on AFL. And by the way, AFL++, you notice these plus plus that I have here. This is a fork by Google from the original AFL. Now, in your lab, you're using the original AFL. Everything will work. Nothing is different, except I will point out there's like one difference that matters to us is a directory path. That's it. But I'll point that out later on. We have to understand the fuzzing mindset. And I think that some folks, when they're first hearing about fuzzing, including myself, it says, well, isn't this just a bunch of negative tests? I already got tests to do that. Well, we expect your program to have graceful failures. Now, a robust program checks and protects against bad input data, but robustness is the whole program itself. So it might not be right at where that data is getting inputted, but it might be down the path somewhere. So we want to make sure your program can handle these things. Now, a graceful handling might be where your program catches this type of bad data and it might send out an error message and then it will exit with a status of something other than 0. Or it might just block that input and keep the program running, keeping honest and saying, well, we're going to maintain that availability in the CIA triad. Whatever it is, your program has control of that. Ungraceful here means what we're talking about, crashes and hangs. As you probably learned in your OS class, a crash is usually where your program, your process is trying to access some protected memory. It could be a seg fault. Well, the seg fault is from the operating system. It's the operating system that's trying to protect the rest of the rest of the system. So a crash is actually a good thing, but not for your program. You don't want that. A hang, well, that could be a possible memory leak or maybe your logic in the program's all screwed up because the input did it and it's just sitting there and doesn't know what to do. Now, we want to fix them as developers. We want to make sure things keep going. But here's the thing. Attackers can use these crashes and hangs as opportunities. They could do things like code injection attacks, denial of service, or DOS. They could even create an exploit from your program to gain access to the system. And you might have heard of remote code execution, etc. They might use something called a buffer overflow where they can inject code, they can get a console or a shell, and then they can, who knows? And they can be able to bypass, say, things like DMC, firewalls, all of those. So this is why we really care about good, robust code. I talked about fuzzing campaigns. Now, fuzzing is usually done long-term, and it's usually testing done in the background. I've heard people trying to put it into CI/CD environments or these continuous integration places, but the issue with that is usually fuzzing is something that's randomized. It's something that's usually long-term, and it's also could be quite resource intensive, etc. That's usually what I recommend. And when you start fuzzing, usually in the beginning, you will find issues, and we call that low-hanging fruit, right? So most of your work probably will happen up front where you're trying to characterize these bugs, fix them, etc. And that's exactly what we want. We want you to fix them as soon as possible. As I mentioned, campaigns can last up to weeks. So some strategies might be, let's say your program has multiple input surfaces, attack surfaces like we call them. You might want to run the applicable fuzzer in parallel. You might have 3 or 4 different, say, AFL fuzzers. You might have one kind of fuzzer that's focused on the user space stuff, and then maybe have another one that might be focused on the networking part, because a lot of our projects might have a combination of these input attack surfaces. Big thing here, crashes and hangs are not false positives. This is dynamic testing. So unlike static code analysis and looking for vulnerabilities that might say, oh, that looks like a potential crash or whatever, but it ends up being a false positive, here we can say that without a doubt it is crashing and you need to fix that. Now, AFL, it stands for American Fuzzy Lop. It's an open source fuzzing tool, been around forever. White box, it instruments the code, and there's tons of documentation, tutorials. This video is one of a billion videos out there, but it works, and that's the great thing. So what does AFL does? Well, it's not a tool that does everything. I don't think there's any tool that does everything, and everything meaning the different types of technologies or attack surfaces that are provided there. For AFL, it is, of course, C, C++. You can use GCC or Clang. It has each of those compilers. It's modified one for each of those compiler types. Of course, you got to have the source code available. And it's directed at user space apps. It could be libraries, parsers, encoders, you name it. Kernel stuff, there's other fuzzers for that. So I wouldn't use AFL here, but there are other tools for kernel stuff. And again, the inputs could be anything. So we talked about APIs and files, etc. It's not designed for network packets or RESTful APIs, websites, etc. And, you know, there may be your project or your program doesn't accept any inputs, or maybe the data itself, the data flows are fixed no matter what. Those probably aren't too interesting to use, so probably not there. Really quick shout out to the AFL Bug-O-Rama. This is from the original AFL, but if you go to their webpage, you'll see this is like a Hall of Fame, and some big programs like OpenSSL, SQLite, Apple, Safari, PHP, all kinds of programs everywhere. Just the list goes on. A lot of victims that AFL found, but you have to look at it this way. These are much better now because of AFL, because they fixed the bugs in them. AFL installation is really simple. All you got to do is, what I recommend, just doing an update. We're in Kali Linux for this, as you know, and you want to install Build Essential GDB GNU Plot, right? And I have a script down here, set up AFL++. It does all of that. Then you're going to clone it, and then you'll CD into the clone directory, which is AFL++, all words this time, run make, and then do a sudo make install, and just run AFL-fuzz, and then you'll see the output, the usage message. That means you're ready to go. Of course, we have to pick a project to fuzz, and I did tell you, I promised you that we were going to be fuzzing a goat, and indeed we are. We're going to be fuzzing FuzzGoat. And FuzzGoat is just an intentionally vulnerable user space application that parses JSON. It's open source. You come here, and you can grab it down. That's all it does. It doesn't do anything, but it pretends it's parsing a JSON file, and it's, of course, doing all of the memory management, etc. with that. So we're going to fuzz those JSON files that FuzzGoat reads using AFL. And the JSON files, the initial thing that we start out with is a file that is a valid file. It should not cause FuzzGoat to crash. And we normally call this initial file the seed. But before we can even file it, we have to compile FuzzGoat, as I mentioned, and we're going to use one of the AFL compilers. For this particular demo, we're going to do AFL-GCC. Now we need to download FuzzGoat and build it and install it, and then we're going to compile it with our AFL-GCC. So just do a get clone in whatever directory you want to. We have it under our exercise directory. CD into FuzzGoat. But before you do anything else, open up the make file and then replace cc equals GCC. CC equals GCC with CC equals AFL-GCC. In fact, I think it's already done for you. But the reason why I put this up is for your Visionaire project, you were using GCC. You would do the exact same thing. Open up your Visionaire makefile and replace your GCC with AFL-GCC. Save and close that file. Run make. Don't do a make install. We're just going to run everything at the local directory as accordingly. I don't know if there even is a make install. Now, when you run make, you're going to see, I got my arrows here. When you see like AFL-AS and AFL-CC, it's being instrumented. You know everything is good. You're going to see an output very much like this as well. I also provided a script called setup FuzzGoat to help you along, and we're going to use that when we're doing the lab. Now, before we actually do any of the fuzzing, we have to do some initial setup. It's pretty easy. Assuming you're still under your fuzzgoat directory, you're going to make a couple subdirectories, one called input and the other is the output. And then we're going to copy a positive test case, as I mentioned. I provided one called good.json. Just copy that good.json, which is under your fuzzgoat directory, to the input directory that you created there. Also, fuzzgoat does come with one called seed.json. You can use that as well. But seed.json actually is not valid input, but good.json is. And then one other thing before we start, you're going to have to configure your operating system to do unlimited size core dumps. Basically, when a program or process crashes, we want it to core dump. We want to make sure it's not limited by size, because depending on what you're fuzzing. Anyway, we just want that to be in place, because then we can use those core dumps later to do debugging. Now, I want to talk about the command line execution and what those parameters mean. So the actual fuzzer is AFL-FZ, or fuzz, AFL-fuzz. -I is your input directory, -O is your output directory. This program is, in our case, fuzzgoat after it got compiled with AFL-GCC. So in your case, it's going to be your Visionaire program as compiled by AFL-GCC. And these purple amp signs here, this is actually AFL fuzz speak, but what it's telling behind the scenes is this is where the input data goes. So, and this is a dummy program, by the way. I'm just saying -F is going to read to an input path, a file, and AFL is just replacing it to its own path, and it's going to derive that good.json. It's going to fuzz it, and it's going to give its own temporary path, which has that fuzz bad data, and it's going to replace it here. That's all what's happening behind the scenes. And then again, that's dummy program. There's a -D argument. So if you have your own program later on, like in our Visionaire, remember we have the uppercase E and a -K for the key, blah, blah, blah. It just shows that you just have everything else as normal, just where you're going to input your stuff. In this case, it's going to be a file. This is what these double @ signs are for. Now, let's go ahead and do it for our AFL++ execution. Before you do anything, just make sure you make your terminal big enough, maybe maximize it. AFL will complain if your terminal is too small. So we like to just, and you'll see it if it's too small, but either maximize or just stretch it out a little bit. And then here's the command, AFL-fuzz, -I input, -O for the output. And then here's our fuzzgoat program. Make sure you have the /fuzzgoat. And then fuzzgoat, by the way, doesn't have any command line key arguments per se. It just takes the fuzzgoat space, the path to the JSON file. So that's very easy here. That's what you put there. Now let it run for a while, and then that's the thing. How long you're going to run it? If you're going to do it for a long time, I recommend if it's on a system that you are not using currently, because fuzzing could take up some resources, or do it overnight. I tell people, don't try to, do other things while you're fuzzing. It may slow things down. And anyway, it's resource intensive. Now, here's the dashboard. This is the cool thing. So this dashboard gives us an indication as to where we are at in our fuzzing. And the thing, I'm not going to go over everything, but it will go over how long you've been fuzzing. So I believe in our assignment, I say 4 hours or so. And then here, the things in red are probably the most important. How many times this thing, or saved crashes there are. So let me go down here to total crashes. And there were 119 crashes within a minute and 20 seconds, which is crazy. But because AFL is super smart, and this is what I love about this tool, it's able to filter it out and say, well, of all those crashes, 15 of them are unique. And it knows that, again, because it understands the code. So if you didn't have that, you would end up looking at 119 files. That would have been bad. Now it's down to 15. So let it run for a while, let it bake. And then to stop this, just do your Control+C. And then we are done. It'll shut down. And obviously the next thing we want to do is find out what we did. And AFL does come with some cool charts that you can use. So there's a tool that comes with the AFL tool suite. It's called AFL-plot. And all you need to do is AFL-plot, and then to your output directory, default. Now this default, by the way, that is one difference from AFL++ to AFL. It's kind of annoying, but that's one difference. So in the original AFL that you're using, it's going to be just the slash output. That's it. And I do have that in the instructions, so the instructions for the lab doesn't talk about default. And then you space, and then you give it any output directory. I'm just going to call it charts. It's going to take and create charts from this. In fact, it creates a web page with a lot of nice pictures, and you'll see in a second. Once that's created, it should be really quick. Then you can run Firefox with the command line, go to that charts directory, and then you're going to read this index.html file. And I use this to put it in the background, to run it in the background. And then I also have a test result script, so you don't have to do all of this. But here's those charts. And this will give you stuff over time. You know, when we looked at the dashboard, we saw a total, but we weren't really sure, are they still coming or not? I didn't run this for very long, but over time, especially this one down here, if you start to see like unique crashes just narrowing out, kind of, I don't want to say asymptotic behavior, but this just flattens out over a given period of time, and you see, say, the edges or levels, everything is just kind of flattening out after a while, that's probably a good indication that you're ready to, you know, stop. All right. The coolest thing about this, of course, is how do I reproduce the crashes? Okay, I've got all these crashes. How do I go and debug them? Well, all of the crashes and hangs are stored under the following directory. So output again, default crashes for crashes, obviously, and output default for hangs. That's where they're at. And as I said before, the old AFL does not include the default directory. But when you do an LS, you're going to see all of these unique crashes. I think, what do we say, 19 of them are unique? Or 15. 15 are unique. So this probably should be about, sorry about that, this should be about 15. I didn't take them all, there's no other ones, but you probably will end up having 15 unique files here. I just took a snapshot of some of them. And all you need to do is, these are actually input JSON files. So it contains the bad JSON file that was introduced into FuzzGoat. So here's an example. You pick any of those files that you want. Your names will differ, of course. In this case, I think I just picked the first one. I run FuzzGoat, and then I'm just giving this crazy full path to that file. And then this was the bad input. And yeah, I didn't like this at all. It was taking, I'm not even sure why that's bad, but it looks like valid. But for some reason, it didn't like it, and it caused a crash from there. So as promised, we are now going to do the demo, and we are going to fuzz the goat. So I'm under exercises AFL++. So do a get poll if you don't see that. Run ls here. You'll see all these different setup scripts. The one that I want to run right now is, I'm not going to go through all of the installation piece. I'm just going to run this setup.all, which will save us some time. So while it's running, what's happening is it's installing AFL, it's installing FuzzGoat, it's doing that initial setup where we're creating the input and output directory. We're taking a file called good.json. That's going to be our first test case. It's a positive test case, which means that when FuzzGoat reads it, it's not going to fail. And also just think of FuzzGoat as your Visionaire program. And your Visionaire program also is going to have this input-output directory. And of course, we're going to have our own command line arguments, but it's going to use a valid input file as its first test case. And I think we were just going to do encryption only, -uppercase-E. So this was it. Shouldn't take that long. And there's going to be this FuzzGoat directory that we're going to go to. So let me go there. And now, before I start fuzzing, I need to modify our makefile. So I'm going to type vi makefile. You can do whatever program that you want. I just like vi. And if you remember your Visionaire program, you're using GCC. So we want to replace GCC with AFL GCC. I'm using as parameters here. I think in your Visionaire program, your GCC is down here. But what you want to do is replace GCC with AFL-GCC in your makefile. And then I'd save it, and I'm going to leave. Now I'm going to clear, and I'm going to make. And one thing you'll notice is pretty quick. You'll see these AFL-AS and AFL-CC sprinkled about in the output. When you see that, when you see it for your Visionaire program as well, you know that you're using the right compiler, and you know that your program is getting instrumented with AFL. All right, now we are ready to fuzz. So we're going to do AFL-fuzz, And you can tell I already did this here, but provide that input, the path to your input directory with the -i. The -o will be the path to the output directory. And then we just do the path to your fuzzgoat. Make sure you do the // the ./, and then fuzzgoat does not take any other parameters except just the path. There's no -f or anything like that. It's pretty simple, and that's where AFL knows where it needs to take that good.json file. When it fuzzes it, it creates a temporary file with the fuzz data, and that temporary file gets these @ gets replaced with that temporary file. So let's do this. Ready to go. And you notice that my window is up and big enough. I think I'm maximized here. But if you get an error that says terminal too small, then you need to make it bigger. Now I'm going to let it run for at least about 1.5 minutes because we need to run it just long enough so we can generate some kind of charts. But in the meantime, let me go over a few things. This is your elapsed time, your run time here. In the lab, I think I said 4 hours. So this is where you would take this picture, or at least 4 hours before you stop it. And then over here, you're going to look at, well, the big ones here, of course, are saved crash in red. But if you come down here, total crashes, you'll notice right now it says 11 saved and 90, almost 100 crashes occurred. Well, this is where AFL is awesome because it knows that many of these crashes are duplicates. So instead of you going in after the fact, and then you're going to be, you're not going to want to look at 120, 130 files when knowing that maybe there's only a dozen or so that are unique crashes. So it filters out the noise pretty well. The corpus count is the number of test cases. Right now it's already ran 130 some cases. As I mentioned before, if you want to increase coverage, you might create a parallel instance of it, maybe even use a different, instead of good.json, maybe another type of JSON file different than that one. And that will give you additional coverage, and that's not uncommon as well. Another thing you want to make sure is down here, your CPU, you want to make sure that it's not like killing your system. If it's at 100% or so, you might want to, well, you either have a better system to do it or let me know, but it should be a little less, maybe 50, 60, but if it's constantly pegged at 100 and stop it, just let me know. All right. With that said, I'm going to head and just do, we're about at 2. Let's let it run for about 2 minutes here. So we have some decent charts. Looks like we already have 16 issues. And I'm going to hit Control C now. And Control C stops it. So we had 147 crashes, 16 issues. And they tell us to have a nice day. Now, what we're going to do is we're going to generate a chart based on our results. So all I do, there's a tool called AFL plot that comes with it. And you can tell I ran that as well. And we just give it to the output directory /default. And then I'm going to put all of the charts under a new directory that I will create called charts. What that is just a, it's like a web page, and then it has a bunch of JPEG or PNG files that show the charts. You'll see that in a second. So next thing, let's take a look at the charts. And I use just Firefox. You can use anything you want, but there's an index file under the charts directory, index.html, and then I'm going to just run it in the background. Let's bring it up. And here's the charts. Now, this is our run that we just did. And you'll see here that the interesting ones, at least in time for me, is that we have the unique crashes here on this line. And this is, again, not long enough, but over time, when you start seeing like they're not increasing, everything sort of flat lines. I don't want to call it asymptotic behavior, that's not the case, but you just start seeing everything flatten out. You're not getting new bugs. There's no new paths that it's getting to. Then basically you can maybe tell yourself, okay, we're done. So I can't say, like, the question is, when are you done fuzzing? This will help you determine where you're at. If you're seeing, even after 4 hours, more and more bugs still being added, then you want to keep it going from there. The last piece I want to talk about, let's get into the output directory just a little bit. There's multiple directories that get created in the output directory. So if I go to default, and you'll see that there's a crashes directory, there's a hangs directory, there's something called queue. If we look at, let's just start with queue and maybe work our way back. These are actual input files. that have, these are test case files. These are files that were fuzzed and derived from that good.json, but they haven't been executed yet. So these are just in the queue, basically. There's a hangs directory, but Fuzzgoat, I don't think ever hang for me. So, but your app may. And if it's a hang, as I said, maybe it didn't respond, it never shut down, should come back after a minute or two, whatever it is, you would get a hang files. But the one that we really think and love to look at is going to be our crashes directory as such. And I forget what it was, like 16 or something. Let's see. Let's do a word count here. 17, yeah, 16, because there's a README file in there. You don't count that. So yeah, we have 16 unique crash files. And what we do if we want to, and we know they're unique, right? So each one should be. And it could be that we have possibly 16 different bugs. Sometimes that's not the case, but worst case, it could be that. So far, at least what we found. Now, if I want to reproduce these issues, let me first show you. I'm going to cat all of the files from there, and I'm going to show you some of the test cases. So we're just going to look at them. Unfortunately, it's going to take that README file too. But yeah, ignore this part. But if we move up to here, here's a bunch of different test cases that we had from those files. And you can see there's a bunch of garbage, unprintable characters, all of those things. All right. Now what I can do, let me come back to my LS, and I want to take the first test case. I'm just going to copy this file, if it lets me copy it. Sometimes it's not happy. All right, and I'm going to change my LS, and I'm going to do Fuzzgoat, because I'm in the Fuzzgoat directory, right? All right, so what I've done here is just take that first file, I run it, and I should get a crash, and I do. There you go. And what's strange when I look at this, this actually looks like a valid test case, but for whatever reason, Fuzzgoat didn't like it. And this is where you can take these files and you can give it to, you can use them for your own debugging, or if you're working with developers, you can give them these test files and they can go back and, you know, tell them to debug their own code. Anyway, that's it. Thank you.